Today I'm going to share an innovative solution that bridges two critical sectors, steelmaking and agriculture, to tackle one of our most pressing environmental challenge, methane emission from rice farming. The title of my presentation is Reducing Methane Emission in Rice Cultivation Using Fe and Slag Silicate Fertilizers, a sustainable approach for agriculture and industry. As we face intensifying climate pressure, we need create solutions that don't just solve one problem, they solve multiple problems simultaneously. What we will discuss today does exactly that. So let's dive into. Let's start with the fundamental problem. Why does rice farming produces so much methane? Rice cultivation typically involves flooding filled with the water. This is done intentionally to control weeds and pests. But there is a critical side effect. The water blocks oxygen from penetrating into soil, creating an anaerobic environment. In this oxygen-starved condition, a specialized microbes called methanogens come to life. These microbes thrive without oxygen and break down organic matter in the soil. But here is the problem. Their metabolic byproduct is methane gas, a potent greenhouse gas that escapes into the atmosphere. This is not a minor issue. Rice paddies are almost the largest agricultural source of methane emission globally. In fact, rice farming contributes significantly to our overall agriculture greenhouse gas footprint. Even that rice feeds billions of people worldwide. The scale of this problem is enormous. But methane emission are just one symptom of a large problem. When rice fields are flooded, we are creating a multiple soil health issues. First, low oxygen availability disrupt nutrient circulation. Nutrient cannot move through the soil effectively. So even if they are present, plants struggle to access them. Second, most rice growing regions have soil that are naturally deficient in three critical minerals: calcium, magnesium, and silica. And these are not just nice to have nutrient, they are essential for soil structure and plant health. The combination of these factors create a cascade of problem. Poor nutrient retention means plants are undernourished despite our best uh, fertilization efforts. Soil acidification weaken the soil's capacity to supply microbial diversity. Lower plant strength means weaker rice plants that are more vulnerable to pest and disease, and ironically these degraded soil conditions intensify methane production. So we have a viscous cycle. Poor soil health drives more methane emission, which further degrades the environment. We need to break this cycle. So this is where the slag-based silicate fertilizer comes in. Let me explain what slag is. Slag is byproduct of iron and steel making. When we produce steel, we process iron ore at extremely high temperature. The impurities and non-metallic compounds in the ore melt and separate, creating a slag residue. For decades, this slag was considered waste, something we had to dispose of. But slag is actually rich in valuable compounds. It contains 30 to 40% calcium magnesium. By weight, it has approximately 35% silica content. Importantly, it contains natural iron compounds. When slag is processed and stabilized, it can be transformed into high quality silicate fertilizers. These fertilizers address precisely the deficiency we identified in rice growing soil. The calcium and the magnesium improves overall soil health and structure. The silica strengthen rice plant stems, making them more resilient, and the iron compounds, which we'll discuss next, plays a crucial role in supporting methane emission. So essentially, we are taking an industrial waste product and converting it into a agriculture uh, asset. Now, the real magic happens with iron. Let me explain the biochemistry methanogens. Those methane producing microbes are discussed use a specific metabolic pathway. They essentially breathe by transferring electrons as part of their energy production. This electron transfer is essential for them to survive and produce methane. Here is the key insight. Iron especially Fe3 plus compete with methanogens for these electrons. When iron is present in the soil, it becomes an alternative electron acceptor. Microbes prefer to use iron because it's energetically more favorable than methane production. What's the result? When iron is available, methanogens are forced to reduce their activity. They have fewer opportunity to compete their methane producing metabolic cycle. The suppression is not absolute. Methanogens doesn't disappear, but their activity is significantly curated. This is the um, fundamental principle that makes iron enhance slag fertilizer to powerful. We are leveraging a biological preference to suppress methane production at the microbial level. So let me summarize the environmental benefit because they are quite comprehensive. First and most directly reduce methane emission mean lower greenhouse gas contribution to our atmosphere. Given that methane global warming potential is 28 to 36 times that of CO2 over a 100-year period. Even a 10 to 15% reduction is highly significant. Second, we are recycling industrial byproduct instead of landfilling slag or using it only for road construction. We are creating a valuable agricultural input. This reduces landfill pressure and maximizes the utility of steel making output. Third, the slag fertilizer directly improves soil quality, better nutrient availability, improved pH balance, enhanced soil structure. These all support healthier soil that can sustain agriculture for generation. Fourth is the stronger rice plant mean better yield, better resilience to pests and disease, and ultimately more food security for farming communities. And fifth, these practices support the broader shift towards sustainable agriculture. We are demonstrating that the agriculture and the industry can walk in a tandem rather than as opposite forces. So it's not just an environmental win, it's a economic and social win as well. So let's focus on the blast furnace slag, especially because it's the most proven option for agriculture use. Blast furnace slag generated from blast furnace iron making process has a very favorable composition for agriculture. It's consistently contain in 30 to 40% calcium and magnesium. It has a highly 35% silica content. It contains natural iron compounds. Here is the critical point. The blast furnace slag has a long established history of use as a silicate fertilizer. It's not experimental. Farmers and soil scientists have been using it for decades in many parts of the world. This gives us confidence in the safety and effectiveness. The data shows impressive results when applied to the rice paddies. Blast furnace slag-based fertilizers can reduce methane emission by approximately 10 to 15% per hectare. For a large rice growing region, that's a substantial greenhouse gas reduction. Additionally, blast furnace slag is naturally alkaline. It helps neutralize soil acidity. Another common problem is rice growing reason. So we get dual benefit, methane reduction plus soil pH improvement. The bottom line is the BF slag is a mature, proven technology ready for deployment at scale. Now, as a steel maker, myself, I want to introduce a second slag source, BF slag, that basic oxygen furnace slag generated from the steel refining process. BF slag has some advantages, contain calcium, iron, and silicon compounds, the same beneficial elements steelmaking produces very large volume of BF slag. So if we could use it agriculturally, we would have abundant supply in principle. Agricultural reuse of BF slag makes sense from a circular economy perspective. However, and I want to be clear and honest here, BF slag presents significant challenges. First, BF slag contain high level of free lime calcium oxide that hasn't fully reacted. If added to the soil directly, this free lime can cause unwanted reaction and soil expansion and pH overshooting, which damages the soil structure and plant health. Second, BF slag composition is more variable than BF slag. The calcium, iron, and silicon content can fluctuate depending on steelmaking condition. This variability makes it harder to predict how much nutrient benefit a farmer will receive. Third, BF slag may contain trace metal oxide that need careful management before agricultural use. So BF slag requires extensive processing, aging, stabilization, treatment, and testing. Before it's safe for agricultural department, it also must meet strict regulatory requirements for soil and crop safely. The takeaway is that the BF slag has a potential, but it requires more development and more careful handling than BF slag. BF slag is carefully our most practical option. So here, where we push the innovation forward, iron enhanced silicate fertilizers, while natural slag contains iron compounds, if we deliberately increase the iron content, adding 2-3% additional iron, we can dramatically boost performance. Why? Remember the mechanism we discussed. Iron suppresses methane producing bacteria. More iron means more suppression. The relationship isn't perfectly linear, but it's robust and predictable. By engineering slag fertilizers with enhanced iron content, we can significantly boost methane suppression to level of 30% or even higher per hectare, enhance the overall nutrient profile, giving farmers better bang for their fertilizer investment. This is particularly valuable in developing regions where steelmaking regions coincide with a major rice growing areas. We can create a local iron enriched fertilizer product that addresses multiple agriculture and environmental needs simultaneously. So we have gone from using a slag byproduct as is to actively engineering it for maximum environmental benefit. That's the future of this technology. So let me step back and talk about the bigger picture, the circular economy impact. In traditional linear economics, steelmaking produces slag as a waste product, and agriculture import synthetic fertilizer made from mine material and fossil fuel. Both sectors generate environmental costs independently. With slag based agriculture fertilizer, we fundamentally reshape this relationship. First, steel making byproduct become valuable agricultural input. Yesterday's waste become today's resource. Second, we reduce the volume of slag going to the landfills. Landfill slag takes up space and requires environmental management indefinitely. Third, and perhaps the most importantly, we create a genuine synergy between two major industrial sectors. Steel plant in agricultural sectors can become supplier of soil health solution. Farmers can become customers of steel makers. These interdependency support region economic development. Fourth, at the national and regional level, these practices directly support climate goal. If India, for example, systematically deployed slag-based silicate fertilizers across our major rice growing regions, we could achieve millions of tons of CO2 equivalent reduction per year. This is the circular economy thinking at scale, solving industrial waste problems while simultaneously solving agricultural sustainability challenges. Now, let me address the geographic opportunity. Asia is home to some of the world's largest steel industry. China, India, Japan, South Korea, Vietnam all produces massive volume of steel and consequently slag simultaneously. Asia accounts for the vast majority of global rice production and rice consumption. Countries like India, China, Vietnam, Thailand, and Indonesia grow rice across millions of hectares annually, and as a consequence of all this rice cultivation, Asia is also a major source of global agricultural methane emission. Here's a strategic opportunity. Countries across Asia have all three elements needed for slag based agriculture solution. Abundant slag supply from their steel industry, enormous rice cultivation across the high methane emission that they are motivated to reduce. This makes slag based fertilizer a uniquely scalable, low cost climate solution for the Asian continent. Unlike more climate technologies that require expensive imported equipment or new infrastructure, slag fertilizers leverages existing industrial capacity and farming practices. For example, like India deploying slag-based silicate fertilizer could simultaneously reduce agricultural greenhouse gas emission, improve rural farm productivity, create new value chain connecting steel plants to farming communities, support both the steel and agricultural sector. This is a win-win situation and opportunities environmentally, economically, and socially. Let me bring everything together. The problem flooded rice cultivation create a anaerobic soil condition where methane producing bacteria thrive. These generate massive agricultural greenhouse gas emission. Additionally, rice soils are often deficient in calcium, magnesium, and silica, driving poor soil health and lower productivity. The solution, slag-based silicate fertilizer, addresses both problems. These fertilizers derive from the steel making byproducts and are rich in exact nutrient rice soil needs. The mechanism the iron ions in the slag suppress the metabolic activity of the methanogens by competing for electron in their energy production pathway. More iron equals more methane suppression. Current status blast furnace slag is proven and nearly for deployment and can reduce methane by 10 to 15% per hectare while improving soil health. BF slag has potential but require more development and processing future direction. Iron enhanced silicate fertilizer can push methane reduction to 30% or beyond, offering superior environmental and agriculture benefit. The big picture, this represent genuine circular economy thinking, transforming industrial waste into agricultural value while simultaneously solving climate challenge. The opportunity is Asia with its massive steel industries and rice cultivation is ideally positioned to lead uh, the global deployment of this technology. In summary, slag-based silicate fertilizers represent a practical, scalable, low-cost approach to reducing methane emission from agriculture while improving soil health and supporting regional development.